Hello everyone and welcome to this Know-How Solutions webinar. My name is Björn Skånberg and I work as Field Application Engineer here at Know-How Solutions. So this is optimization of embedded software's energy consumption. So the agenda for today, I will start with a motivation. So why would you like to do this? Then I will talk a little bit about the requirements. So both the requirements of the Lauterbach hardware that you need, but also something about the CPU that you are measuring on. Then I will present to you a solution, so what you can get out of this measurements. And then I will end with a hands-on live demo from the tool. So if you have any questions, please type them in the chat box as the webinar goes along, and I will answer them at the end. Okay, so motivation. So as you all know, energy is equal to the current multiplied by the voltage multiplied by the time. So in application, each of this parameter can be influenced by the software. So we can use things like dynamic power saving modes. So if the CPU has nothing to do, it should go down to sleep to reduce energy consumption. We can dynamically change the frequency of the CPU. So if you have a task, would it be more beneficial to have a high CPU frequency and then do the calculations in shorter time? Or would it be better to reduce the CPU frequency and do the calculations a little bit longer and perhaps save some energy? There's also the possibility of change dynamically the voltage of the target. And we can also control within the software dynamic use of chip internal and external resources, so such as RAM, flash, and so on. So as a software engineer, we have to constantly search for the optimal settings of these three parameters. So it would be good to know which part of the software is typically power hungry. It would be good to know which parts of the hardware is typically power hungry and also what the software is doing at that time. It would be good to detect if we are using some kind of power saving modes in the wrong way. Also, it could be good to see if we have unexpected power peaks. So if we have an unexpected power peak, then we can see what software was doing at that point in the time. So basically, we would like to do calculations of energy consumption. So both for overall level to see how much energy we are consuming, but also we would like to see it on different RTOS tasks. So how much energy is each task taking, but also to see down on function level, sorry. So how much energy is each function consuming. So how the program changes will affect the power consumption. So what we can get out of Lauterbach is that when we have done the measurements, we can have a look at the different functions. So which function has been executed, how much energy have they taken in total. We can see how many times they were executed in our measurement, and also the min, the max, and the average amount of energy consumed. Together we have that with the program flowchart, so we are able to see how the functions are calling each other, and we are also able to draw the voltage waveform. So if you have dynamically setting of the target voltage, this can be drawn as a function of time, and of course the current, so how much current is your CPU consuming, and this can also be drawn as a function of time. Requirements. So to do energy profiling, this is possible for every architecture. So you need from Lauterbach and from Lauterbach hardware, you need a hardware that is able to do trace recording and that we can attach an analog probe. So this can either be a power integrator, the Power Trace 2 from Lauterbach, then of course, the Combi probe or the microtrace. So when you're using this Lauterbach hardware together with the analog probe, you will get time correlated measurements of the program flow, current and voltage. So this is then controlled within the Lauterbach GUI, which is called Trace32, so no need for an extra GUI to do energy profiling. So we need to attach an analog probe. With the analog probe, we are able to measure 4 different voltage inputs, and we are able to measure 3 different current inputs. So it has a 12-bit resolution and sample rate of 625 kilohertz. Solution. So first of all, to do voltage measurement, you can connect the analog probe directly to the voltage of the chip and to the grounds of your target, and then in that manner measure voltage if you have dynamically changing the voltage. We can do current measurement. So if you have an eval board, you typically sometimes have a shunt resistor. So you are able to measure the current using this shunt resistor connected from VDD and then into the chip. And then you need to be connected to ground, of course. However, what I think is the best solution, and the solution that I'm using today, is that I have built an external adapter which holds my shunt resistor. So measuring again VDD and into the chip and then ground. So once I have connected the analog probe to my target and to the Lauterbach, I need to configure and tell which channels I would like to use. So I need to say which of the 4 voltage channels and which of the 3 current channels I would like to use. So if, let's say, I'm using channel I2, I need to tell Trace32 the value of the shunt resistor. So how many ohms is this? And then, of course, when I have both the voltage and the current, then I can measure the power. So because the power is the voltage multiplied by the current. So then if I measure P1, for instance, I can get the current from I1, and then I can either say that, okay, I have a statical voltage, so I'm not changing the voltage of my target, which you then put 3.3, or you can use V1 as an input parameter. So you can use, if you have dynamically change of the voltage, you can get this in your power measurements and get the time plot out of that. You are also able to export and save the data for later analysis or create a report. So you can store your trace buffer with the program flow, and then you can store your, let's call it, energy buffer, where you have your current and voltage measurement. Then you can store it to your hard drive, and then you or your coworker can load this energy buffer, the trace buffer, and the application onto the simulator mode. And then you can look at the results again, and you can debug your application using the trace buffer backwards and forwards and looking at the energy consumption. Or you can create a report. So if you have done some measurements and you have, let's say, functions, how much energy each function is taking, then you can quite easily create a report with this command. Handson. So for today, I'm using an eval board, the MCB STM32F400. So this is a Cortex M4 with a float point unit. On top of it, I have a RTOS from ARM, which is called RTX. I have the both debug and instruction trace available. So since I'm using the Cortex M, I have the ARM IP block, which is called Embedded Trace Macro Cell, which is creating the program flow or the instruction trace for me. So if you have a Cortex A and you would like to do the same measurements, then you need to trace the PTM, the program trace macro cell, and that will provide you with instruction trace. If you're using PowerPC, then the hardware block is called Nexus. So different name, but they will provide you with instruction trace. Then I'm using the Lauterbach hardware called MicroTrace to pick up the trace. And this is a 256 megabyte of memory. So the MicroTrace is a low-cost option for those of you who are looking to do debug and trace and energy profiling for a Cortex M microcontroller. I have the analog probe connected, and then my target is set to 3.3 voltage, so I'm not doing any dynamically changing of the voltage. So this is how the analog probe looks, and this is the, let's call it, schematics of my adapter, which I have created. So I just, for pin number 1, I have I2 minus, for pin number 3, I have I2 plus, and this is measured over a shunt resistor, which has 1.5 ohm in resistance. So the commands that are involved when doing energy measurements is, first of all, I need the CI probe command group, which allow me to configure the channels that I would like to use and how I would like to collect my energy buffer. I'm able to draw the signals as a function of time, and then I can do energy statistics function. So I'm able to tell which function and how much energy it has consumed, and also on which, let's say, RTOS task, so how much energy each RTOS task is consuming. So let's go into the Handson. So before we do that, just share the contact info. So for technical questions, please contact me. And for sales questions, please contact one of my coworkers. Okay, so let's open Lauterbach. So I have Lauterbach up already, and I will run my start script. I would like to use Lauterbach to flash my target. Yes, please. So my start script will flash the target. It will initialize the trace. It will load the debug symbols to the debugger, and it will open some windows for me. So let's open the trace buffer, and let's open the analog probe buffer. So I have set my trace to be collected in FIFO mode, and I have set my analog probe to be collected in FIFO mode. So as you all know, FIFO is first in, first out. So when the buffer is full, the oldest record will be overwritten. If I want, I can change both these methods to stream, and then streaming the trace buffer and the energy buffer from my Lauterbach hardware to my PC, and then it's really the size of the hard disk of my PC that determines how long I can go on and do measurements. I have had my startup script to configure the channel which I would like to use. So the startup script told Trace32 I would like to use channel I2, and I have a shunt resistor of 1.5 ohm. Then I'm using power channel 2, which takes I2 as an input, and then it will be, the value will be multiplied by the statical voltage for my target, which is 3.3 voltage. Okay. So I will go ahead and run my application and collect measurements for a few seconds, and then I will show you the results and what data we can get out of this. So we're running, and we stop. So I have collected a little buffer in the trace, and I have collected a little buffer in the energy measurement. So let's go ahead and look at the ATA stat function. So this is telling me how much energy each function is consuming. So I see that in total I've spent 1 joule on this measurement, and 36% of the energy was spent in Trigo, and 63% was spent in the OS idle. First of all, sorry, let me just tell a few things regarding my application and what we're looking at. So the application I'm measuring on is using a RTOS which is called RTX. So I've made Lauterbach aware that I'm using this RTOS, so therefore I will get the RTOS awareness menu. So this will show which tasks I have in my system. It will show the state, and I'm also able to show the stacks. So how much is the maximum consumption of the stack and how much are we currently consuming. So depending on the RTOS that you are using, the menu will look slightly different and the things you can look at will be slightly different. So in my applications, I have a few tasks that are writing to the LCD screen, which I have on board. So I will expect that this writes will cause a peak in the energy consumption. I have one task which is executing a function which is called Trigo, and this is using the float point unit. So I will expect this to cause an energy peak as well. And then if my CPU has nothing to do, he should go down to sleep to reduce the power consumption. Okay, so first of all, what we're going to look at is how much energy each function is taking. So we see here that Trigo takes about 37%, and we see that idle is around 62%. We can then also see how much time we spend in each function. So as you know, how much time you spend in each function is not necessarily equivalent to how much energy we spent in that function. So we see we are spending around 75% in idle and only 25% in Trigo. So Trigo is a quite power-hungry function. So perhaps there could be some potential in optimization the Trigo function to reduce the energy consumption. So if we have a look here in the list, we see we have a function which is called common. Common has been called 24 times. We see that we have a minimum, we have a maximum, and we have an average value of common. So how much energy it spends in each function call. So it could be quite good to know who has called common. So if I go ahead and click on linkage, I see that common has been called 12 times by X echoes, 4 times by linker, 4 times by echoes of Osirian, and 4 times by the root. So I can also see that the average is quite similar for common, independent of which function that called common. So this is good. So then I don't have any particular power peaks here. So if I now have this window, and I think this is something that I would like to share with my coworkers and in my company, I can of course create a report out of this. So the reports that are available is XML, PDF, ASCII, and comma-separated format. So I created an example of this yesterday, the energy per function. So this is in XML, and this will create a quite nice overview of how much energy was spent in each function. So to open this window, this report, you don't need to have Trace32 installed, which is quite good. So anyone can open it. So basically every window that I'm showing today, and you feel like, okay, this is something that I would like to have as a report, it is possible to export as a report. Okay, so let's dig into the application now. So I have set up the window where I draw the power, which is the green curve, and the current, which is the red curve, to be in sync with the trace chart function, so the program flow on function level, so basically how the different functions are calling each other. And then I have the trace list. So the trace list is showing which instruction that has been executed. So when I click in one of the windows, the other two will follow. So this is quite good when I'm examining my application. So let's have a look and see what we can get. So as you see, I have quite regular power peaks here, and if I measure the distance between two of them, I see it's about 10 milliseconds, so I suspect this is the SysTick causing this power peak. So if we go in and have a look in the trace chart, we see that the blue line here is equal to where the blue line is here. So this is due to the SysTick handler that is causing these small power peaks. I see I have larger power peaks. So if we zoom in, I can see that it's both for the SysTick handler, but there is something else also executing here. So if we follow the gray line, we see that we have a function here, which is the LCD set window from the task called clock. So this is causing a little bit larger power peak, but this is also expected. So if we zoom out a little bit more and we have a look here, we have also a power peak. So is it the same or is it a different? And yeah, we see this is also when clock has written to the LCD. Then as you can see, I have a quite large power peak here. So this takes around 380 milliseconds, and as I suspect, this is the trigger function which is causing these large error, which is causing this large power peak. Okay, so then I know why I have the different power peaks and what causes them. So I can of course compare the MIPS, so the million instruction per second, with the power peaks. So just because you have a lot of MIPS happening in a point in time does not necessarily mean you have a high energy consumption, and just because you have low MIPS in a point in time does not necessarily mean you have a low energy consumption. So you see that it's going quite well, so both the MIPS and the energy consumption. But as you can see, if you have the power peaks when you're writing to the screen, the MIPS of the CPU is very low, but you have a a quite large peak. So this is the type of things which you can find when you're using this energy analysis. So also we are able to say on task level, so if we would like to know how much of each RTOS task, how much energy it's consuming, and also how much time we spend in each RTOS task. So as you see here in the RTOS task of idle, we spend 63%, and we spend 37% of the energy in the demo, and the demo task is the one that holds the trigger function. But if we have a look at the timings, we see that only 25% of the time is spent in the demo function, which holds the trigger function. So this is the type of measurements which you can get out of Lauterbach. So I think this is all I had to say, all I had to share with you. Thank you for listening, and I will start answering the questions.